When you think of the Earth's oceans, lakes, and rivers, and many of the other liquids that you use every day, it can be hard to believe that liquids are the least common state of matter in the universe. Liquids are less common than solids and gases because a substance can only exist in the liquid state only within a relatively narrow range of temperatures and pressures. In this lecture, you will examine the properties of the liquid state and compare them with those of the solid state and the gas state. These properties will be discussed in terms of the kinetic molecular theory. First main idea: the intermolecular forces of liquids determine their properties. A liquid can be described as a form of matter that has a definite volume and takes the shape of its container. The properties of liquids can be understood by applying the kinetic molecular theory. As in a gas, particles in a liquid are in constant motion. However, the particles in a liquid are closer together than the particles in a gas are. Therefore, the attractive forces between particles in a liquid are more effective than those between particles in a gas. This attraction between liquid particles is caused by intermolecular forces, such as dipole-dipole forces, London dispersion forces, and hydrogen bonding. Liquids are more ordered than gases because of the stronger intermolecular forces and the lower mobility of the liquid particles. According to the kinetic molecular theory of liquids, the particles are not bound together in fixed positions, but move about constantly. This particle mobility explains why liquids and gases are referred to as fluids. A fluid is a substance that can flow, and therefore take the shape of its container. Most liquids naturally flow downhill because of gravity. However, some liquids can flow in other directions as well. For example, liquid helium near absolute zero is able to flow uphill. Relative high density. At normal atmospheric pressure, most substances are hundreds of times denser in a liquid state than in a gaseous state. This higher density is a result of the close arrangement of liquid particles. Most substances are only slightly less dense, about 10%, in a liquid state than in a solid state. However, water is one of the few substances that becomes less dense when it solidifies, as we will discuss in section 5 of this chapter. At the same temperature and pressure, different liquids can differ greatly in density. Relative incompressibility. When liquid water at 20 degrees Celsius is compressed by a pressure of 1,000 atmospheres, its volume decreases by only 4%. Such behavior is typical of all liquids and is similar to the behavior of solids. In contrast, a gas under a pressure of 1,000 atmospheres would have only about 1/1000th of its volume at normal atmospheric pressure. Liquids are much less compressible than gases because the liquid particles are more closely packed together. Like gases, liquids can transmit pressure equally in all directions. Ability to diffuse. As discussed in last section, gases diffuse and mix with other gas particles. Liquids also diffuse and mix with other liquids, as we see on the screen here. Any liquid gradually diffuses throughout any other liquid in which it can dissolve. The constant random motion of particles causes diffusion in liquids much as it does in gases. Yet diffusion is much slower in liquids than in gases because liquid particles are closer together. Also, the attractive forces between the particles in a liquid slow their movement. As the temperature of the liquid is increased, diffusion also occurs more rapidly. The reason is that the average kinetic energy, and therefore the average speed of the particles, is increased.
Diffusion is a process where the random motion of molecules causes a movement from high concentration to low concentration. For example, when food coloring is added to this beaker of water, there is initially a very high concentration of dye molecules where the food coloring droplet hits the water. In the rest of the beaker, there is no dye in the water. After time, the dye molecules mix randomly with the water. Finally, the dye is spread evenly, and the concentration of food coloring is the same throughout the water.
Surface tension. A property common to all liquids is surface tension, which is a force that tends to pull adjacent parts of a liquid's surface together, thereby decreasing surface area to the smallest possible size. Surface tension results from the attractive forces between particles of a liquid. The higher the force of attraction, the higher the surface tension. Water has a higher surface tension than most liquids. This is due in part to the hydrogen bonds water molecules can form with each other. The molecules at the surface of the water are a special case. They can form hydrogen bonds with the other water molecules beneath them and beside them, but not with the water molecules in the air. As a result, the surface water molecules are drawn together and toward the body of the liquid, creating a high surface tension. Surface tension causes liquid droplets to take on a spherical shape because a sphere has the smallest possible surface area for a given volume.
Surface tension is the inward force of attraction between molecules in a liquid. The distance between molecules tends to favor the state with the lowest possible energy. For simplicity, imagine that each molecule is a ball. From the graph, we see that there is an optimal distance between a molecule and its neighbors, which lowers the molecule's energy. The lowest possible energy is achieved when the molecule is completely surrounded by other molecules at this optimal distance. In surface positions, however, there are fewer neighboring molecules, fewer opportunities to achieve a lower energy state. Consequently, molecules on the surface have higher energies than those that are not on the surface, and try to move to positions of lower energy. The result is surface tension. Because of surface tension, droplets form. This minimizes the surface area and thus the number of molecules in a higher energy state. We see this also in the rounded tops of condensate on glass, and when liquid splashes. Surface tension keeps the water in this glass from overflowing. If we sprinkle pepper on the water, surface tension supports it. Some substances, however, can disrupt surface tension. If a surfactant, such as soap, is added, the pepper sinks.
Capillary action, which is the attraction of the surface of a liquid to the surface of a solid, is a property that's closely related to surface tension. A liquid will rise quite high in a very narrow tube and will wet the tube if a strong attraction exists between the liquid molecules and the molecules that make up the surface of that tube. This attraction tends to pull the liquid molecules upward along the surface and against the pull of gravity. This process continues until the attractive forces between the liquid molecules and the surface of the tube are balanced by the weight of the liquid. Capillary action can occur between water molecules and paper fibers, for example. Capillary action is at least partly responsible for the transportation of water from the roots of a plant to its leaves. The same process is responsible for the concave liquid surface, called a meniscus, that forms in a test tube or a graduated cylinder.
Capillary action is the attraction of a molecule on the surface of a liquid to the molecules of the surface of a solid. Because of capillary action, liquid moves up this very narrow capillary tube. When fluid flows up a tiny tube or piece of paper, it is the result of the attraction between the liquid and the surface of the solid, combined with the liquid's surface tension. The liquid will rise until its weight balances the pull of gravity. The same process is responsible in part for the transport of water from a plant's roots up to its leaves.
Evaporation and boiling. The process by which a liquid or solid changes to a gas is called vaporization. Evaporation is a form of vaporization. Evaporation is the process by which particles escape from the surface of a non-boiling liquid and enter the gas state. A small amount of liquid bromine can be added to a bottle, and within a few minutes, the air above the liquid bromine turns a brownish red because some bromine molecules escaped from the surface of the liquid. These molecules became gas molecules, or bromine vapor, which mixed with the air. A similar phenomenon occurs when you apply a perfume to your wrist. Within seconds, you become aware of the perfume's fragrance. Scent molecules evaporate from your skin and diffuse through the air where your nose detects them. Evaporation occurs because the particles of a liquid have different kinetic energies. Some surface particles with higher than average energies can overcome the intermolecular forces that bind them to the liquid, and then they can escape into the gas state. Evaporation is a crucial process in nature. Evaporation removes fresh water from the surface of the ocean, leaving behind a higher concentration of salts. In tropical areas, evaporation occurs at a higher rate because causing the surface water to be saltier. All water that falls to the earth in the form of rain and snow previously evaporated from the oceans, lakes, and rivers. Evaporation of perspiration plays an important role in keeping you cool. Perspiration, which is mostly water, cools since the higher energy water molecules escape by evaporation. This means that the average energy of the remaining liquid molecule is less, thus cooler. Boiling is the change of a liquid to bubbles of vapor that appear throughout the liquid. Boiling differs from evaporation, as we will see in a future section. Formation of solids. When a liquid is cooled, the average energy of its particles decreases. If the energy is low enough, attractive forces pull the particles into an even more orderly arrangement. The substance then becomes a solid. The physical change of a liquid to a solid by the removal of energy as heat is called freezing or solidification. Perhaps the best known example of freezing is the change of liquid water to solid water or ice, which occurs at 0 degrees Celsius. Another familiar example is the solidification of paraffin at room temperature. All liquids freeze, although not necessarily at temperatures you normally encounter. Ethanol, for example, freezes near negative 114 degrees Celsius.
When the temperature of a liquid is reduced, the molecules slow down and are attracted to each other. As the molecules get closer together, they don't have enough energy to break free of their neighbors, and the substance freezes.
At this point, you should be able to describe the motion of particles in liquids and the properties of liquids according to the kinetic molecular theory. Discuss the process by which liquids can change into a gas, as well as define vaporization, and discuss the process by which liquids can change into a solid and define freezing.